Welcome everybody on Zoom. Welcome everybody in the lecture hall. Today we are going to explore white column stores. It's a new technology. I will motivate it. We had trouble today setting up the laptop because it was Murphy's law. You know, everything that can go wrong goes wrong. So the laptop doesn't work. The phone doesn't work. We are stuck outside because of the authentication. So we are going to make it work thanks to one of you there. We are going to monitor the Zoom chat. So you just need to raise your hand, you know, whenever there is something on the chat to make sure, and then I'll just read it directly. That will be fine. Okay, so as always, I will start asking you a question to check your knowledge of the previous time, and then we'll move on with the material. So let me switch over. All right, here's the question. It's a long one, but we'll take the time to do this together. I'm zooming in a bit. So these are XML documents, and I'm asking whether or not they are well formed, including the namespace rules, meaning that everything is correct. In order to not trap you, I was careful to, you know, put all the namespaces at the top and so on, as I taught you, but you need to figure out what doesn't look right in these documents. So you need to select those that are well formed and to not select those that you think are not well formed. So the question has started. I will also project a bit on the screen so that you see them. So, oh, of course, I need to optimize the size. So these are the first two that you can see on the big screen. Then I'll scroll down a bit. These are the first two documents. All right, let me scroll down to 3 and 4. These are documents 3 and 4. Then we have 5 and 6. Normally, you can see it, I assume, on your computers and on your phones as well. And the last one, 6 and 7. $25 answers already coming in, 33, 51, 7. Who needs more time? Please raise your hand if you need a bit more time. Right, let's not block quite yet, but just look at the answers. All right. So the majority is correct, right? So congratulations on that. So now I need to show you what's wrong. Who can tell me what's wrong in the first one here? You can also speak on Zoom if you want. What's wrong in the first one? Yes? Maybe the microphone, the catch box. There you go.
Because we declared P1 twice, the same with for P2.
Exactly. We are binding the same prefix P1 and P2 twice, and that's not okay. You cannot do that. You can also only bind each prefix just once to a namespace. So this is not okay, and this is why it's wrong. The second one is perfectly fine. In fact, it's a textbook example of a document that has 4 namespaces, nicely declared at the top, alphabetically sorted, and so on and so on. So best practice. All right. The third one is a textbook example of how is it called when there is no prefix. What is the name for that? Yes, go ahead. Maybe the catch box.
Isn't it the default or the absent of name?
Yes, it's the default namespace, exactly. That's called the default namespace. So this happens when you just write XMLNS in the root and everything that doesn't have the prefix is in that namespace. So yes, this one was correct too. What's wrong with this one here, the third one? We have raised hands? No? Yes, I see a raised hand over there. You can throw. Don't hesitate to throw. It cannot break. Yeah, that's what it's for. Okay.
We are using namespaces P1 and P2, but never declare them.
Exactly. More precisely, P1 and P2 are prefixes, but they are not bound to any namespace. So you cannot use a prefix if it's not bound. So this is the problem here. We basically declare a default namespace. We don't even use it because there's prefixes, and the prefixes are not bound. So this is what's not okay. What's wrong with this one, the fourth one? Anybody on Zoom too? You can answer. I see the chats. Anybody sees what's going on here? Yes, over there. Go ahead.
We have P2 column B column B. That's not well formed.
Exactly, that is not well formed. You can only have one column, and what's on the left is the prefix, what's on the right is the local name. But if there's 2 columns, then this is not okay. It doesn't mean anything, and that will be refused. So that's also a correct answer. The next one is absolutely fine as well. And the last one is also fine. What happens? In what namespace are the elements in the last one here? Yes, go ahead, the catch box. Throw it far away. Yes, oh wow.
No namespace. Like a no namespace.
Exactly, it's in no namespace at all. Exactly, because there is no default declaration. Very good, you made it. So this is what I wanted to test today. So now I'm going to switch over back to the slides. All right. So just to make sure, again, because I said we have an issue with the laptop of the moderation, but if you ever see, you know, a red number on the chat and so on, just you know, wave at me and interrupt me, and then I'll make sure to answer. All right. Okay, this should be familiar with you. This is the big data stack that we are rebuilding. We actually did quite a good job already, right? We looked at the storage. We look at at cloud storage, object stores, and key value stores. We looked at HDFS, which is a distributed file system. And we also, well, we didn't look at it, we just brushed it up. It's the relational database management systems, the good old ones that sit on a single machine, right? Okay, oh, this I already did. Today, we are going to start going one level up with some modeling, but it's still some physical data models. It's not yet the logical ones, but I decided to put it on that layer, basically, but you will understand soon. I'm going to start with a bit of history of what happened, I would say 20 years ago. the engineers of some large companies who had a lot of data, and here understand Google, Facebook, Twitter, Yahoo, and so on, the data no longer fits in a relational database. They tried to improve the system to make it work, right? Because it's too small, there is a single machine, so even if the data exceeds the size of the hard drive, you already have a problem. So you could scale up, right? By adding more CPUs, by buying more RAM, by buying a larger disk. But the most you can do today is 26 terabytes, right? With a single drive, right? So it doesn't bring you very far. Okay, so you could scale out. That's an idea that people also had back then. So to put it on several machines. But remember, this is 20 years ago. We don't have yet this whole Hadoop and so on developed yet. So in order to scale out and put it on multiple machines, what the engineers thought is, let's install an instance of this relational database management system, maybe PostgreSQL, MySQL, Oracle, IBM, SQL Server. Let's install that on plenty of machines. Let's buy 10, 20, 100 machines, and we install a copy of this relational database management system on every machine. And then what we are going to do is two things. Actually, these are now very natural to you because we saw them, but we basically shard and we replicate. Sharding means that some of the data is going to store on this machine right here and some other data on that machine right there, nicely sitting in the relational database management system of the machine on which you put it, right? You can also replicate, meaning that you can store the same data on 2 or 3 machines and so on. But the problem is nobody would do it for you. So the engineers who started building that sort of things had to write themselves in a host language the code that would connect to the machines and spread the data. When you want to look up data, you also need to figure out on which machine it is and so on and so on. So that was actually very complex. And even what's worse, the maintenance cost of that are absolutely enormous. You need to figure everything out. It's hard to set up and so on. Of course, when I'm showing that to you now, we've learned HDFS. So you know a lot of how this can be solved with the name node, the data nodes, and so on, right? But back then, they tried to scale it up manually and build basically gluing together plenty of relational database management systems. So the idea of HBase, so white column stores, is to replicate this abstract model of a table. So it's going to be a relational table or a tabular structure. But on top of a cluster of machines, it's the spirit of data independence. Instead of viewing tables on every machine and then gluing it together in code, we do the opposite. We view one single table on top of the entire cluster, and the logic that deals with that in order to distribute the data is hidden in the implementation. This is exactly the spirit of HBase, right? And what's more, we are going to end up storing the data on top of HDFS. That's great news. We know HDFS, right? So now we'll study how it works together with HBase. But this is an even better motivation, I think. So this was a bit of history just to show you the challenges that engineers were facing 20 years ago. Now, you could think that we've already solved that kind of problems with plenty of technologies we've looked at so far. Remember object stores, Amazon S3, Azure Blob Storage. Remember HDFS. Remember DynamoDB, so the key value stores. So basically, we looked at technologies. But the problem is, there is always something that is wrong in there. So you see here, we have the throughput, the latency, whether you can update the data, whether you can store bigger values than what would fit the typical value that would be atomic. Larger collections, can you handle billions or trillions? And random access, can you access a very specific portion of the data somewhere? And you see, in the case of object stores, it's great at throughput. It's great at storing larger values, up to 5 terabytes, because you put whatever you want in there. And the large collection, it's worldwide S3, right? But random access, no, in the sense that you can, of course, select an object, but within an object, looking at a specific part it's not meant for that. You could, but it's not optimized. Low latency, no, it's already 100 to 200 milliseconds in S3. We are nowhere near the latency of a relational database management system, which would be a few milliseconds. Updates, no, you can just put another object instead, and that's it. So you see, these are weak points. What about a relational database management systems? Well, it's low latency, you can update the data, you can have larger values. These are called clubs and blocks, right? Clubs is character large objects, and blobs is binary large objects, clubs and blobs. Larger collections, no, because this sits on one machine. So maybe you can go to 1 million. You can go today to 1 billion because now we have more space, but back then 1 billion was unthinkable for a relational database management system, certainly not trillions. Random access, that works. And high throughput, no, this is also not optimized for high throughput. HDFS is optimized for high throughput. But latency on HDFS is bad. You already feel, if you use it on the command line, it takes 1 second every time you execute a command in there. Updates, also not. You can create new files, you can append, but you cannot modify the data in place. You can have larger values, yes. You can have very, very large petabyte files, larger collections as well. If you put JSON lines in there, for example, that also fits on HDFS. And random access, no, you cannot easily, at least it's not optimized for random access in HDFS. So what about key value stores? Well, key value stores do have random access. You can very quickly, in just a few milliseconds, look up a value. You can have larger collections. You can have billions or trillions of values in a with a distributed hash table algorithm, quote. You can have larger values. No, that's a no here, because we saw that it's 400 kilobytes tops in a key value store in DynamoDB. Right, so the order of magnitude of 1 megabyte. This is actually not so large. Updates, yes, you can update with put and delete a key value store. Low latency, yes, a few milliseconds. High throughput, no. In a key value store, you don't do scans. You can just get and put, but that's it. It's not even sorted, right? So the notion of scanning through an entire key value store to aggregate stuff is not part of the design. So you see there's issues everywhere, and we cannot really combine all these advantages together in any of these technologies, right? Well, I have good news for you. This is pretty much what we are going to try to do today with white column stores. We are going to try to build something that is a hybridation of all of that achieves everything. The throughputs, low latency, you can update data, you can have larger values, you can have larger collections, you can have random access, and so on, right? So is it clear to you, the motivation? What we're achieving? All right. So now I'm going to take the same approach as I'm taking every week, because I just want to keep saying, I love saying data independence, data independence, data independent. It's all over the place in that course. So for the spirit of data independence, I'm going to start with the logical data model, just like I did with HDFS, in previous technologies. And then we'll look into the physical architecture. I'm going to give you a word of warning on the physical architecture, just so that there is no surprise. The physical architecture part of white column stores is one of the toughest part of the entire course. So if you find it, complex to understand, or that it doesn't all add up, already today, don't worry, because this is tough. I know it's tough. Now you know it's tough as well. So you know what to expect, right? But I'll take my time. We'll take the time to walk through that, and I explain how it works, because even though it's tough, there is an incredible amount of things you can learn from the design of white column stores that are not just useful for white column stores. These are actually very useful techniques and tools that are used at plenty of other places. And even for a computer scientist, knowing these things is actually very important, right? So you will see it's very, very informative, and it's going to be worth the effort. But before going in there and scaring you with the physical architecture, I'll start with the logical model. So it all started really with Google's Bigtable. That was the original proprietary software. With the idea that if you have a tabular model, a database, in high normal form and so on, third, for example, joins are expensive, right, in general. Selecting, projecting, we'll see even when we advance in the lecture with MapReduce and so on, that this is easy to do, but the joins are actually expensive. So we want to avoid them. So we are going to denormalize But what this means in the context of big data is that we store together what is accessed together. If you denormalize and join, then everything is going to be together on the same row. So this is an example of a high normal form. So in that case, Boyce code, which I think is 3.5, the normal form. So we have a table with people on the left and city and state on the right, and we can join them. You know, if I join on the city and state, I get that. But this is no longer in normal form. There is repetition, there is duplication with all the anomalies that you know, right? But in fact, in big data, this is what we prefer. We prefer that because now, since all is joined, you can directly read one line all together. It's already pre-stored together. You don't need to join anything anymore. Again, what I want you to remember is that joining that is costly. And if you already pre-join, which is the same as denormalizing, then you don't have this cost anymore. All right? So the idea is that instead of storing the data across multiple tables as we would do in a typical relational data management system, we prefer to store things that way pre-joined. What does it mean concretely and in simple terms? It means that in a table, there are going to be more columns, many, many more columns, because if you join, that increases the number of columns. Well, now you know why it's called wide column store, right? We are going to have many columns. And this is pushing relational database management systems outside of their design scope, because in a typical relational database management system, you typically don't allow more than 255 or 256 columns, right? This is your limit. But here you can have many more than that, maybe 100, 1,000, maybe even 1,000,000 columns, right? So we denormalize things. So you see, denormalizing doesn't just mean you have trees. Last week, I focused on the trees and the fact that you have XML and JSON and you have nestedness, but denormalizing also means that you do that sort of things by joining the data. You're still in first normal form, but you're no longer in the second or third or Boyce code normal form. All right, so this is what we prefer there. Who is following? Okay, now let's go to the model of the software, of the technology. So the idea is we have a table that's not new to you. We have columns, we have rows. Every row is identified with a row ID. This is something that you don't have in a relational database in the sense that what's the equivalent of that in a relational database? What would you call it in PostgreSQL, for example? The row ID. The primary key, exactly. And the primary key can be any column, right? You define your schema, you define your attributes, and then you say, okay, the primary key is this column or is this column and that column, right? But in the case of HBase or wide column store, you cannot do that. You cannot just decide on what column is your primary key. There is one column, the first one that is special, that's called the row ID. And in the case of HBase and Bigtable, it's exactly one column. Cannot be two, cannot be three. It must be exactly one. A counterexample would be Cassandra, which is another wide column store. With Cassandra, I think you can have multiple columns in the row ID. But in the case of HBase and Bigtable, it's just one single row ID. Well, since you do that, it probably starts tasting like the key value model, right? Because you basically have a key, which is the this row ID on every row, and then the value is just the rest of the row, right? So you have the ID 002, for example, here, and then this would be the value associated with this idea. So you see, it smells a bit like DynamoDB in the sense that we have key values. It smells a bit like relational databases because we have a table. It also will smell like HDFS and cloud storage in the scale that it's going to take, right? So I hope that this starts becoming clear. The other thing about row IDs is that they are sorted. There is an order, and this is sorted. You can see I was careful in the way I put them in there. This is by increasing row ID. This is also very important. We'll come back later on what it means for the physical architecture, right? So there is an order in the row ID, and they are sorted. Okay. Next, this is also another thing that differs from relational database management system. Yes, we have a question. Maybe the catch box.
So you just said each row has a unique row ID and the IDs are sorted. But I'm wondering how those row ID are assigned and how they are, how do you determine their order?
Mm-hmm. So this is a burden that is pushed to the user. So you as the user of the system when you insert the key values or the rows, you give the row ID, right? It's your responsibility. So it's not automatic in any way, right? So it's just like DynamoDB, right? In DynamoDB, it's the same. You also give the key and the value when you insert something, right? Does it answer your question?
Thank you.
All right. So it's not automatic is the main message. All right. And by the way, I can maybe tell you that already now. The reason why they look scary, because, you know, as primary keys in a relational database, you could use integers or dates or strings and so on. But here we use some hexadecimals, hexadecimal would be 60, hexadecimal base 16. So this looks binary, right? Well, in fact, it is binary, right? I'll come back to that. But these are really binary. This is just sequences of bits in there. But of course, you can also use strings, right? If you use strings encoded as UTF-8, that gives you a sequence of bytes that you can store in there. All right. Okay. Let's now move on to the next thing I want to show you. In a relational database management system, you would have attributes that are the rows, right? Well, in a white column store, we have the notion of column family. It's a group of columns that fit together. I'm using colors in there, so yellow, blue, red. So these are column families. And the attributes within the column, they belong together, so to say. If you want to understand column families intuitively, remember that this table was obtained, for example, by joining multiple relational tables because you denormalize. In a way, each column family could be seen as coming from a different table, right? So we join together something that was a blue table and a yellow table and a red table. We put them together and we get that. It's very intuitive. It doesn't necessarily apply in every scenario and so on, but just it gives you an intuition of the fact that it would correspond in a relational database management system to several tables. But that would be here column families. Okay. Now, when you build a new table in Bigtable or in HBase, you specify the column families. You explicitly create the column family. So you say there is a yellow, there is a red, there is a blue column family. What you do not specify is the names of the columns, the attributes. Now, this is not in relational database management systems, because in relational database management system, you are obligated to provide the name of all of the attributes and their domains, right? But not here. Here, you don't even know in advance what the columns are going to be named. There is no such thing. So ABC, 1, 2, and so I'm using the Latin alphabet, the Indo-Arabic numerals, and the Roman numerals just to distinguish by family. But this is dynamic. This happens while we actually populate the table, right? And finally, I kind of already told you that for the row IDs, but it's actually for everything. Everything is binary. It's all arrays of bytes everywhere, right? Yes? Maybe it's over there, Catchbox.
Do we have to provide the number of columns per group? Or is that dynamic as well?
It's dynamic as well. You don't even have a limited number of columns. You can have 1 million if you want, dynamically.
Okay,
It all works. Yeah. I will come back on the architecture. It will all make sense when I show that to you. There is no longer a limitation such as the one in relational database management systems where really you are blocked in terms of the number of columns. Here, you can create them on the fly all you want, right? Did it answer your question?
Yes, thank
Awesome.
you.
Thank you. All right, so everything is binary. The row IDs are binary. The headers, A, B, C, the names of the columns, the names of the column families, everything is an array of bytes, right? There is no types, there are no integers, dates. HBase doesn't know any of that, right? It's all binary. But of course, you can still, as a user, decide that you store integers or dates or strings or what you want as binary. But the thing is, it's your burden as the user to deal with that. HBase will not know about that, so it's all going to go into your Java or Python or whatever host language you use to access HBase, all right? So this is why it's really a physical storage system, HBase, more than a full-fledged database system. That's how to think of that. Does it make sense, all binary? For whom does that make sense? All right. And also here, an order of magnitude. I said we can store larger values. So yes, larger than in DynamoDB or key value stores. Key value stores was 400 kilobytes. The sweet spot for HBase would be up to 10 megabytes per cell. So you can really squeeze. I was about to say a big, it's not big, it would be medium. Let's call it medium size. So you could squeeze some medium size XML or JSON document in there. You can squeeze an HTML page in there. You can squeeze pictures in there, all the way to 10 megabytes per cell in there. So this is optimized for that. In a relational database management system, you could hit it with a hammer and squeeze very large quantities. There are protocols known as Toast, for example, in order to implement that. But it's not optimized for that sort of things. In the case of HBase, it is optimized for that. So you can go all the way to 10 megabytes. It's a soft limit. There is no hard limit of 10 megabytes. It's just that if you go beyond that, then you are pushing the system a bit to its limits, you know, and then it might start slowing down or not working as you expect, right? But basically, just the order of magnitude, 10 megabytes. Consider it as intermediate. So small would be an atomic cell in a relational database, right? It's an integer, it's a date, it's a string, and so on. This is medium. It's an HTML page. It's a bunch of XML documents, a bunch of JSON documents, right? It's bigger. And then you have the really large things, which is an HDFS file or an HDFS block or an object in S3, right? So just to give you the orders of magnitude. All right. So this is the model. We have a question, I see. So let me go over. Can a column be part of multiple column families? Can column families overlap? By design, no. By design, they cannot. The reason is actually very simple. In order to identify a column, you need the column family plus the column name. So if you have two columns that have the same names, it's like two people having the same first name. You distinguish them with the last name, but they are still two different persons. So this is why it doesn't overlap, and a column is always within a specific family, identified with the family plus the name, or the qualifier, it's also called. Does it make sense? I'm assuming yes, right? Okay, I'm assuming yes. Let's continue. So this is the model. Now I'm going to move on to the queries. How do we query the system? So some of the aspects of querying will not be new to you because we've seen that before. For example, you can get a row specifying a row ID. This is something we saw in cloud storage, in object storage. We saw it in key value stores that you can do that. So this is not new. You can get a row given its row ID. You can also get only specific column families. You don't have to get the entire row. You can say, I only want the blue and the yellow, right? For example, associated with row ID 0A1. So this is get. Then you have put. Put is also not new. We have that in S3, we have that in DynamoDB. You know, this is just saying, okay, now here's a row ID. I want you to put these values in there, right? And then you send as a user the content of the cells. It doesn't have to be for all the column families. You can also only decide to put in the yellow and the blue, for example, but not in the red, or you can do it later to populate the red column family, right? So this would be put. This is all binary again. All the values in there, as far as HBase is concerned, these are all binary values that go in there. Okay? Scan, this is new. This is something that we didn't really see before. And this is actually going to be super useful when we study MapReduce and Apache Spark later. This system allows you to scan through the entire table and go through all the data. It's especially useful to do analytics. So you start with 000, go all the way to 4A2, and then you can execute code scanning, or you can return the results that are in there. You can aggregate and so on. You can also specifically scan only a column family, or you can scan only a specific interval of row IDs. Right? This is something you cannot do with DynamoDB. Because in DynamoDB, remember the protocol is based on hashes, right? Every key is hashed, And thus, it's all randomly distributed in the ring, the logical ring. So you cannot do a full scan in that way over an interval of keys in DynamoDB. But in HBase, you can. It's actually optimized for that sort of things, right? So you can scan. And finally, you can delete. You can say, please remove all the values associated with that row ID. Again, you can also decide to only delete specific column families for a row ID or everything, okay? And we are done. 4 of them: get, put, scan, and delete. That's the basic model of HBase. So what have we learned here? We have 2 clues that this is a low-level and physical system, not as high level as a relational database. The first clue is that everything is binary. So this is not very abstract for the user. You're pushing that down back to the user to deal with types. And the second clue is that all it does is get, put, scan, delete, which is low level. We are not talking here about selection, projection, group by, order by, which would be higher level. This is very low level. So this is really a physical storage system, but organizing things as a table. Yeah, I see a question on Zoom.
I can say, we had a question from the chat. Can you please repeat how adding a column on the fly works?
Yes, absolutely. Let me go back. Okay. So the idea is that you could say, imagine this is the current table. It's looking like that. And you decide to add a new row. Let's call that your new row, I don't know, 200, right? So the row ID would be 200. So we insert a row right here. Let's say we want to insert the purple values in the purple column family. What does it mean to add columns efficiently on the fly? Is that I'm going to instruct HBase to add a new row with row ID 200, column A with value 1, column B with value 2, and column D with value 3. And that works, and it's fast. I just added column D on the fly. This is what happens. D was added on the fly. There was no other row that contained column D, and I just created it. And I didn't need to modify a schema like alter table, add column you do in PostgreSQL, for example. No, I didn't do that. All I did was inserting a new row that just so happened to have a column called D. It's that simple. And by the way, I didn't add any value for column C, and that's fine. It's not even creating a null as you would do in a SQL database, just not adding anything for column C. Did I answer your question? And I'll come to you.
He has a follow-up question. So there's no requirement that a new column has the same namespace?
Has the same namespace? Column family. How can I put it? You cannot, as far as I know, at least in the design, create column families on the fly. So you cannot just arrive and say, okay, now create this row, adding some, I don't know, green or pink or you know, whatever color new column family. You cannot do that. You can create new columns on the fly within the existing column families. Adding a column family is costly. You can do it. That's more of a metadata operation on the entire collection that you create a new column family. But if adding columns on the fly must be within the existing column family families when I say that. Does it make sense? Zoom?
Last or another follow-up. So request adding a new column request needs to mention a column family as well.
Yes, absolutely, always. Yeah, but this is maybe this is the way I explained it that maybe didn't make sense. Is that when you have this get, put, scan, delete, and so on, you always use column families when you do that, right? If you don't say anything, it's all column families. If you get it all column families, you can restrict to a column families. This is kind of the granularity of the access to HBase is the column family. It's something that's going to be very intuitive when I explain the physical architecture. Then it's going to all add up to you. But basically, yes, when you have a request, you do need to specify the column family when you add a value.
Another question is, does the get return all column and column family tuple for that row ID?
Yes, by default, except if you as a user specifically request only specific families, then it's only going to return them. But other than that, it's returning everything, right? All right, maybe just because there was also a question there, we'll alternate a bit. So let's go to you, and then we'll come back to Zoom. So that's
okay. Actually, it's a two-part question, but essentially with scanning, I suppose when someone looks for a range or with get, we look for a specific row, we need to know the IDs, or do we have any sort of querying functionality where we look for something specific? And
you need to know the ID.
Yeah, so that's one thing. And then for scanning, because you mentioned we can scan between ranges, can we do, let's say, multiple ranges at the same time, or can we go like, I don't know, 3 values from here, 3 from here, and then that in the same scan, or?
Let me do a tentative answer as I understand it. In the case of HBase, I think you need to do multiple scans if you want multiple ranges. So it's 1 range per scan. There are other more recent technologies. I actually have a few slides at the end about that, like newer technologies at Google, where they actually support multiple ranges at the same time at the storage level. So they call that tablets. But in the case of HBase, I think it's really optimized for a single range in the query. Right? At least it's my understanding.
Thank you.
Right? You're welcome. Let's come back to Zoom.
Does a row with a specific row ID span over multiple column families, or can the row also be restricted to a specific column family?
You can. So technically, in terms of, let's speak in terms of constraints. In terms of constraints, whenever you add a new row, you have the possibility to add columns in all of the column families that exist without any problem and without performance costs. You can also decide to only add data in one of the column families in a specific rows, right? It's just that you didn't make use of the fact that you were also allowed to add to other column families, right? So you can, but you don't have to. Did that answer the question? Okay. All right, any more questions before we move on? Yes, we have one more there. That's further, let's try, let's see. Wow, impressive.
Okay, so when we delete from data from one column family, then what happens to the same, to the same rows in other families? Or when we add to one column family, what happens to the same row in other column families? There's just like nulls, or they are empty, they are not specified. What happens?
I'm going to start with an orthogonal answer, but then you will understand why I'm answering that way. So my answer is going to be orthogonal to what you asked. What we are looking at here is the logical level, right? It's a logical, like consider it math. It's the beautiful world of math where we look at the families and the row IDs. So technically, if you only look at the math, when you delete the data corresponding to a row ID and that is in a column family, mathematically, all you do is remove the data with that row ID and family. It has no impact on the rest of the row in other families. It's still there, and it has no impact on the data in the same family in other rows, right? However, what ties the column families together or the row would be at the physical level. It would be an implementation level, right? In terms of performance. For example, if you only delete or add data to a specific column family, what's going to change is not going to be the semantics of the system. It's going to be how fast it is. If you only access one column family, you'll just see that it's faster, as opposed to accessing all of the column families. Why? You'll understand as soon as we look at the physical implementation. But the way to interpret this is very important. This is one of the what I'm trying to transmit to you in terms of the way to look at any database system. You always need to distinguish the logical level from the physical level and reason on what's happening on the logical level, meaning the semantics of what's happening in the mathematical model, everything that happens on the physical level, of course, is there for the correctness of the logical level. It makes sure that it actually produces the effect that you want. But the other effect that is not part of the math is the speed. It's going to be fast, it's going to be slow. This is what's going to make a difference. Of course, mathematicians don't really care about that, right? But computer scientists do care about the speed. Okay. Did I answer your question in that way?
May I have a follow-up?
Yes.
So could we interpret that basically the row ID with every column family is kind of like key value store? So like in this case, we would have like free key value stores here. Could we interpret it that way? Or
yeah, logically, absolutely, yes. So let me repeat to be very precise. With math, you can absolutely say all of that here is a key value store. A key value store, not in the sense of DynamoDB, a key value model, let's call it a key value model, where this is the key right here. And all of this together is the value. Right. Now you can also, because this, let's call it the mathematical freedom, you can also consider that we have 3 key value models, one of them for this family with the key associated with that value, then another one with the key associated with that value for the yellow column family, and a third one with the key associated with that value for the red column families. Mathematically, it's equivalent, right? You just either have a single model that joins everything together, or you have 3 distinct key value models. Right?
Thank you very much.
Right. Thank you. Right, I don't see any more raised hands or in Zoom. Let me check the time to make sure that you get your break. Oh, you should get a break. It's already 3. So we're going to stop here. I'll give you back the 2 minutes. So we'll start at 17 past 3 for the continuation of the lecture. See you in a bit.